Good afternoon. I'm Alexander Richter. I'm a PhD candidate in chemical engineering from NC State University. I'm in the group of Dr. Orlin Veloff. And we have invented environmentally benign nanoparticles with antimicrobial functionality. And this project is a collaborative project with the US Environmental Protection Agency. So how did I come to the STEM field? As a kid, I participated in a school trip to Biochemie Kundl. It's now owned by Sandoz. And I learned about Brundtle's and Margreiter's invention on the first acid-stable penicillin, penicillin 5. And what this invention enabled was, for the very first time, the oral delivery of life-saving penicillin. Just a short note on penicillin. This growth plate shows bacteria growing here outside where the white is, and here where it's transferred, basically no bacteria is growing because of the antibiotic, because of the penicillin. Now, over time, what happened is actually that some bacteria evolved and exhibit broad-spectrum antimicrobial, basically resistance to antibiotics, and this happened more and more. Overall, this invention actually made me want to pursue a STEM education, especially to develop better antimicrobials. So how can we solve the problem of antimicrobial resistance? Well, let's take a look at nanoparticle technology. What are the most widely used nanoparticles in industry today? It's actually antimicrobial silver nanoparticles. They are used in products such as disinfectants, consumer products, even skin creams. And they are valid because of their broad-spectrum antimicrobial properties. They can basically deactivate bacteria, fungi, spores, algae, and other microbes. Well, but taking a more precise look at them, actually, the US Environmental Protection Agency told us that there's an issue with these particles. And this is, okay, they have the desired antimicrobial function, but when released into the environment, they have a persistent design, they have a metallic core, and what may happen is that there's the active post-utilization, affecting bacteria, affecting aqueous animals in the environment. So the challenge is, how can we reduce the amount of silver of such a nanoparticle system, while upholding, obviously, the desired antimicrobial properties, while reducing active nanowaste or increasing post-application safety? Well, when the problem is, let's say, the metallic core, what about if we replace this metallic core with a biodegradable core? Well, let's take a look at this idea and concepts which is shown here. Of course, silver nanoparticles can perform desired action. They release antimicrobial silver ions. However, their persistent design, their persistent core may stay active in the environment, releasing silver. Our particles can perform the same desired antimicrobial action as silver nanoparticles because we employ highly active silver ions. However, these particles have a biodegradable core, increasing post-utilization safety. Once the core, which is lignin-based, is released into the environment, it would degrade according to pathways available. The potential outcome is less silver, time-limited activity, and of course, increased post-utilization safety. All right. Of course, with every invention, one has to test how it works. This is just an example of the proof of concept. It shows a growth media and E. coli growing here, where the white spots are. Basically, a reference plate shows growth of bacteria, and we want to get rid of them. We treat one sample with our invention, and we can see that our invention deactivates the E. coli in this case. We made multiple tests on 3 other bacteria, and overall, we established that these particles, our invention, has higher antimicrobial efficacy. They just need 1/10 of silver by mass, with some bacteria only 1/20 of silver by mass to do the same desired action, which means we can now reduce the amount of active chemical introduced into the environment by 90% by mass. We can reduce it by 90%. We only need 10%. And on top of that, we have a degradable design. All right, so how do we get to such an invention in the field of chemical engineering? especially nanoengineering, so to say? Well, one has to fabricate the particles. There are different synthesis methods available. One has to functionalize the particles. We have heard that previously. One has to optimize the particles, in this case by surface modification, changing its surface charge, changing its hydrophilic, hydrophobic properties. One has to do rigorous proof of concept testing, and in this case also a safety evaluation, which was then performed by a third party, in this case by the US Environmental Protection Agency. One has to work through all these steps, and one has to solve all challenges. All right, so now we have an invention. If you want to commercialize it, or if you want to have these properties in a product, what's going to be the next step? Well, we have to file a patent. So let's take a look at the invention itself in a simple way. In principle, we have a biodegradable core, an active ingredient, which may be silver, which may be copper, and a surface modifier. We have three components that provide a strong patent basis. All right, so in this case, actually, NC State filed a patent application for this invention, US patent and an international one. But it doesn't stop there. Once one has a patent, to interface it with industry, one needs a corporation, or one needs to directly license it to a corporation that products can be developed. So in this case, we actually formed a startup company, Benova Incorporated, to license back the exclusive rights of this technology, and we now seek the development of this technology. All right, there are multiple target markets for this technology. One big one is the crop protection industry. If one looks at the crop protection industry, in general, the world population is increasing by 200,000 people every day. It is estimated that to meet global demand, food production needs to increase by 70% by 2050. This is also reflected in the growing crop protection market. It's a multi-billion-dollar crop protection market. If we look in detail, actually, in one specific market, in this case, vegetable farmers, we see they are not happy. They use a lot of crop protection products, but they still lose, on average, 37% of their crop, while basically also having a burden on arable land, seen here. So we have actually here three challenges: growing need, or basically growing need for food. We have technologies that don't work well, and we have huge environmental burden because of crop protection chemicals today. There's a need for more sustainable crop protection products here, and our technology could here provide a solution. All right, if you focus on this market with our technology, let's take a look at the properties for this technology for the crop protection industry. The next step, of course, here is to make, again, proof of concept tests. In this case, application-specific proof of concept tests. This graph shows samples on top, drying time here. And we see here, for instance, one sample, a hydrophobic dye, which basically would be a potential active ingredient. If it dries, it builds a clump. What that means is that the surface area to volume ratio is fairly small. It cannot interact well with microbes or with a target. It may just fall off a plant or the part of the plant it needs to protect. Whereas if you see here with particle-assisted drying, we see that basically we can actually increase the spreading properties of this active ingredient, which obviously would relate to a higher biocidal efficacy. All right, if we take these properties, we basically would then make a value proposition for the crop protection industry. In this case, one technology property is obviously increase of surface area of the active ingredient. And that relates, obviously, to enhanced biocidal activity. One problem that can be solved is, of course, to counter antifungal tolerance that has been observed in some products. Another property, as we have seen, is particle-assisted drying to reduce clumping, increase spreading. Another one is particle adherence to surfaces. This is to reduce runoff, specifically. Overall, these particles could potentially enhance the biocidal efficacy and reduce cost of crop protection products. If you look at products that where this technology would be applicable, of course, it's an antifungal crop protection product, a spraying solution, simple as that. Antifungal seed protection, also a big field, and in the future, anti-nematode root protection. Advantages, go from decreased pesticide runoff to better distributed actives. Overall, of course, if one reduces the amount of chemicals, one has a cost reduction. One also has basically a reduced environmental impact, and potentially with this technology, of course, a better treatment against pests. Overall, I want to give you that advice, basically to, in general, if one takes on projects that involves many fields, to seek collaborations in a positive and constructive way for better results. And that may be, regardless in what field you work, it may be also regardless what position you have, if you're the project leader, sub-project leader, team member, or perhaps you're a team member in one project, but a project leader in another. And I also want to give many thanks and credit to Professor Orlin Veloff, my PhD advisor, and as example also here all the collaborators that were involved with the project, many of course from NC State University, that's basically where I'm from. And especially I want to point out here enthusiastic undergraduate students that worked on this project, Hinton Armstrong and Joseph Brown, who really also brought this project forward. Also, NCSU Tech Transfer and Partnership Office for providing laboratory space to develop the technology towards products. And of course, the US Environmental Protection Agency for funding and the safety evaluation of the particles, as well as our collaborators in industry and academics. I would also like to thank the Lemelson Foundation, the Lemelson-MIT program, and the Lemelson family to enable an event like this. Thank you very much.
If I may ask, are there any disadvantages to using what you're creating compared to what you currently use?
So basically what these particles have, they can temporarily increase the efficacy of a biocidal active ingredient. And this will be related to time-limited activity. So the time it will be active will be shorter, depending on the application. And it depends on the application. It can be a benefit, or it can also be that one actually has to increase, obviously, the loading in the particle to counter that out, that one has a longer activity time.
So just looking at your design in general, a question, is silver a 100% effective antibacterial agent, or do we need to develop stuff after using
Excellent
silver?
question. The question relates to silver, if that is, let's say, a broad-spectrum antimicrobial agent. The simple answer to that is yes, there's no antimicrobial resistance be reported towards silver. So basically, yes, it's an effective broad-spectrum antimicrobial agent.
It's really a cool project, but can you speak a little more about the biodegradability and the time course? Clearly, do you have different products depending on the time that is needed, or have you thought about those things?
Okay. Of course, we have thought about that. We took materials basically that are biodegradable. Basically, we have a lignin-based core. In this case, indolent AT lignin from the paper industry, a byproduct, or high-purity lignin from the biofuel production as a byproduct. We, by ourselves, have not made biodegradation tests, but literature says that these products obviously will biodegrade. Actually, if one looks at lignin, if it biodegrades, so lignin, just short as a note, lignin is a biopolymer. It's found in plant mass. 30% of wood is basically by mass is lignin, and the other major component will be cellulose. Cellulose and lignin actually degrade slowly in the environment. However, with lignin, what it constitute, if one looks actually, especially in the forest, one can see that it's actually what constitutes basically humus. Basically, it would be a fertilizer afterwards. That's how it biodegrades.